All right, here we go in 3.2 with the life cycle of stars. This is where things get a little bit crazy. So we'll start off with where they're born. They are born in what are called nebulae. So that first word is the plural. Otherwise, it's known as a nebula. A nebula is a huge cloud of dust and gas in space. A lot of matter just kind of floating around. Gravity of the gas and dust pulls everything inward. So what'll happen is you'll get some little clumping that'll happen, and because that has a little bit more gravity, it'll start to pull other things in towards it, and eventually those clumps get bigger. Small cores of material accrete and have more gravity, so now you're getting things that are larger and larger. As the cores get larger, they smash together, so now you're getting bigger chunks that are then hitting and fusing together. I shouldn't say fusing, it's not fusion, but they're sticking together. Now it starts to heat up. When you get more and more of that material, it gets hotter and hotter, and this is where we get into what's called a protostar stage. When there's enough gas and dust, nuclear fusion will begin. That's when there's so much mass that these atoms in there are hitting each other with so much speed that they are actually fusing. These helium or hydrogen atoms are fusing into helium. Stellar ignition is the point where fusion causes the star to shine. So it's kind of like the switch gets flipped on. Fusion gets going and the star ignites and starts giving off heat and light and radiation. So there are two main options. There are the average stars and there are the massive stars. So if you look at the top, you'll see what is considered an average star, like our sun. It'll be born in the nebula. It'll work its way up to the main sequence and it'll live there for maybe billions of years because they're generally small. Then you will expand into a red giant, so they get a lot bigger. Then they will turn into what's called a planetary nebula. That's where the outer shells blow away from the inside. And what's left is basically the core, a dense core called a white dwarf. Now, if it's a bigger star, now massive, so we're getting quite a bit more massive than our sun, it has another option with two possible outcomes. So here you take a massive star, it will expand into a red supergiant, so a very, very large star. This one will have a larger explosion, what's called a supernova, where the outer layers explode away with a lot more force than just a planetary nebula. Here they're basically expelled. Here they're exploded. And then what happens is the material that's left will implode on itself, and it'll either turn into a very super dense neutron star. These are very dense. Or, if it's large enough and massive enough, it could turn into a black hole. Yes, black holes are real. So here's your average star life cycle. So these are, these main sequence average stars. Most stars are average. The smaller the star, the longer its life. So small little red dwarfs can live billions and billions of years. Our star is kind of in this area, its main sequence. It'll probably live about a total of 10 billion years. We're about halfway through its life. So some, they think, that are even smaller, way down here in the corner, could possibly live trillions of years. Now, there's no way of knowing yet because obviously we've only been around for 14, 15 billion years in this universe, but they think it could potentially live that long. That's how long fusion could keep going. Most of the time, they will be on the main sequence. So most stars live out their life, most of their life right here. They spend most of their lifetime right in this span. Main sequence stars. They fuse hydrogen into helium. So one like our sun is fusing hydrogen into helium. You've heard that multiple times now. 90% of its life will be spent in the main sequence. So it'll be there for most of its life, and that's where it is right now. We're at about 5 billion years old, about halfway through life. The mass of the star will determine its length. So smaller stars will live longer on the main sequence, and larger ones will be there for less time. Hydrostatic equilibrium. This is an interesting thing. Gravity is always trying to collapse a star. It's trying to squeeze it inward. But there's outward pressure caused by fusion. So all that that's going on inside the star is pushing out while gravity is trying to pull in. If something lowers the outward pressure, the star will contract because gravity will win for a little while and it'll start to pull and smush that star in. But eventually it'll hit a new equilibrium because it'll hit a point where that pressure will then balance out and it won't be able to shrink in anymore. And maybe it'll contract and expand a little bit over its life. When it runs out of fuel, it begins to expand. So it actually starts to get bigger as it runs lower and lower of fuel. So if we have a star close to the size of our sun, so this is what ours would undergo. it will swell. It'll get bigger. It'll turn into a red giant because it's out of hydrogen. And it'll take up perhaps as much space as all the way out to our orbit, where the Earth is. That's how much bigger it will get. The outer layers of hot gas will expand away and become a planetary nebula. So they'll just keep expanding and they'll just kind of blow right away from the star. The core will collapse. So gravity is going to pull it inwards until there is that hydrostatic equilibrium. And it'll be very dense, very small. And then it'll slowly cool over billions of years until eventually it turns into a black dwarf. It's giving off no light anymore. Now, if you have a star that's bigger than the sun, so maybe 7 to 20 times more massive, so quite a bit bigger, when it's out of hydrogen, it starts to fuse the heavier elements. So now helium is fusing, and it's fusing heavier elements all the way up to iron. Iron is the heaviest element formed through fusion. The heavy elements will build up in the core. When it starts running out of fuel, it will swell into a red supergiant, so it gets huge. Gravity will cause the outer layers to be pulled inwards. So now what will happen is it starts to swell. Gravity will pull it back in, and it'll start contracting on itself, and then it'll hit a point where it can't, and it'll actually explode. So the mass smashes the center. That's the implosion, and then it rebounds in an explosion at high speed. So the whole outside blows away. This is referred to as a supernova. Type 2 supernova are the most common core collapse supernovas. So that's that inwards, and then all of a sudden it just blows out. The explosion creates elements heavier than iron. So that's where we get everything beyond iron, where we get some of these bigger elements all the way up to like uranium. The hot gases expand, and a neutron star is often all that remains. A neutron star is incredibly dense, extremely dense, very dense. This is the Crab Nebula. This is the remnant of a supernova where there was a star somewhere on the inside and all the outer layers blew away from it, exploded violently. So this is what you have left, and it's still expanding outwards. Now we get to the weirder part. What if the star is like 20 times as massive as the sun? So a very massive star. Like smaller stars, it's going to burn all its hydrogen, and then it's going to start fusing its heavier elements up through iron again, just like the other ones. Like in smaller stars, it'll also swell into a red supergiant. When the collapse of this one happens, there's more mass. So when it collapses in on itself, it's far more violent. And once it gets going, it's like a runaway freight train. It just doesn't stop, and it keeps imploding, and it keeps imploding. And it keeps imploding, and the outward force of all the elements inside can't actually stop this inward implosion. The collapse never ends, and that's what a black hole basically is. It is a star that has collapsed upon itself and never stopped collapsing, and it collapses into a small point, depending upon how big the star was, it'll determine how big the black hole is. So here are a couple different black holes. This one is a very large one. So here's the size of Pluto's orbit, and that black hole is even bigger. This is a very, very massive one. This is something that you would imagine in the center of a galaxy. And then there are other ones that are smaller. So maybe, the diameter of our sun, and they can even be much smaller yet. These are just a couple that we can actually see from the Earth. All right, and that should wrap up our discussion on the life cycle and the death of stars.